Yeah, thank you, Romain, for the introduction, and of course, Romain, Tobias, for the invitation to be here. It's a great place. Well, I hope that indeed in my tutorial I will give you a proper impression about how important, how exciting the field of terahertz magnetism and terahertz spintronics is. I will also talk further about antiferromagnets to continue the ideas of the previous session. And, well, thinking why terahertz, why antiferromagnets, like we have seen already nicely introduced in the previous talks. Antiferromagnets, well, these are magnetic materials which were discovered in the 20th century, but also the whole modern understanding of physics of magnetism, the breakthrough in this understanding is associated with development of quantum mechanics, also happened in the 20th century, and this all started with the discovery of spin nearly 100 years ago, and then soon it was realized that electron-electron interaction is spin-dependent, and this spin-dependent part of the electron interaction we write these days as exchange interaction, which is simply scalar product of two spins and exchange constant J. And depending on the size of the exchange constant, we have either ferromagnetic materials where all spins point in one direction, and then we can introduce net magnetization. Net magnetization has the very same symmetry as the magnetic field. That's why we can control magnetization with the help of external magnetic field. We can read out a magnetic state of ferromagnets detecting magnetic fields. And soon it was realized also that next to materials which are ferromagnets, we also have antiferromagnetic materials with the opposite sign of the exchange constant, with the antiparallel alignment of spins, where, well, in many antiferromagnets, net magnetization is 0. And in order to describe magnetic order of antiferromagnets, we introduce so-called Niel vector, antiferromagnetic Niel vector, which has different symmetry. And in particular, if you calculate scalar product of the Niel vector in magnetic field, it is 0. So based on this, already based on this, you can see that antiferromagnets shouldn't produce magnetic fields. It's not clear how to detect antiferromagnetic spins. It's not clear how to control spins in antiferromagnet. It was a reason for Louis Niel to state in his Nobel Prize lecture that antiferromagnets are also very interesting, but fundamentally, but seems to be useless. Nevertheless, times, as we've seen, times going further, and these days when we see that nowadays data storage technology is based on ferromagnets predominantly, but nowadays data storage technology is approaching its limits simply because we are willing to write information faster and faster, but ferromagnets, they simply cannot keep up with these rates, simply because the fastest and the most energy efficient way to reorient spins is, of course, to employ spin resonance. And if you look at the frequency of spin resonance in ferromagnets, it's in gigahertz range. That's why the fastest and the most energy efficient way to write magnetic bit in a ferromagnet is just to employ this resonance, and it will take roughly 1 nanosecond. Well, with advantage, of course, that it can still be done by magnetic fields. In antiferromagnets, as we have seen, this time scale is faster, but the problem is that, well, it's not clear how to do this. So if it was possible to control, it was known how to control spins, how to detect spins in antiferromagnets, it would be a great proposal to make a recording medium out of these materials, but still, how to control, how to detect, and how to do this how to control spins in antiferromagnets ultra fast, these are the questions that people ask again and again, and we have seen it in the previous talks that it's also it remains to be these questions remain to be very important and heavily debated in science, and these are exactly the questions I would like to talk about. And I would like to start first how to detect spins in antiferromagnets. And well, first of all, here I would like to make a statement that many things also, I mean, this is a very old topic, and then the very old means that's really old topics, meaning that it's older than me even. And so even it was started soon after the discovery of antiferromagnetism. So Dzieloszynski himself, and later Borevik, Romanov, and Turov, they developed symmetry approach to treat magnetic phenomena in antiferromagnets. They describe symmetry approach to treat properties of antiferromagnetic materials. And here I made a copy of 2 books, like Symmetry and Magnetism. It's nice book written in English where main concepts of symmetry analysis explained. And this is unfortunately not translated book from Professor Turov. It's called Symmetry in Physical Properties of Antiferromagnets. And here I would like to pay your attention to this particular point group of the crystal. And you ask me what it is. The answer is it is an altermagnet. So, and you can see 2001. So the people were interested in these type of materials from the very beginning, or nearly from the very beginning of antiferromagnets. Well, one of the first works dedicated to the materials where we can expect interesting effects which allow us to detect the direction of antiferromagnetic vector, for instance. This is, of course, hematite. So this is a paper from, as you can see, 1957 from Professor Zhelezhinsky. It's about hematite, where he introduced, where he describes magnetic structure of this material. And you can see this has 4 types of spins. And we can define magnetization vector for this material. We can define antiferromagnetic vector for this material. And what Zhelezhinsky showed, that by symmetry, if you apply symmetry element to, for instance, magnetization and antiferromagnetic vector, by symmetry you find that Lx behaves absolutely the same way as My. And Ly behaves in absolutely the same way as Mx. That's why Zhelezhinsky proposed to write the ratio between these two quantities, Mx and Ly, connect these quantities with D, with these days we call Zhelezhinsky constant. And this was the way to explain so-called weak ferromagnetism in antiferromagnets. But the statement I want to make that in the materials like with magnetic structure of hematite, Mx is transformed in the same way as Ly. And well, then you can then continue in this direction, and then you can think, for instance, about antiferromagnetic Hall effect in hematite. So what is Hall effect? So here I show the picture. This ZX plane. You apply electric field in the Z direction. There is a current, normally current in the Z direction. But if you apply magnetic field in Y direction, or there is a magnetization Y direction, you can expect Hall current. And this Hall current is explained or Hall effect in general by antisymmetric part of the conductivity tensor, sigma. So this is a current density, electric field, conductivity tensor. So antisymmetric part of the conductivity tensor basically defines Hall effect. And we can ask ourselves if a Hall effect can be sensitive to the antiferromagnetic vector. Well, it can be. Well, first of all, it's sensitive to Hy component of magnetic field, obviously. It is sensitive to My component of the magnetic field. But then, as I said, if by symmetry My is transformed under symmetry operations of this crystallographic point group, is transformed in absolutely the same way as Lx, nothing forbids us to write here Lx. So what we do, we write this. And someone can look at this and speculate about antiferromagnetic Hall effect. So now the question is, when do you think antiferromagnetic Hall effect in hematite was measured for the first time? Any guess? I told you the field is very old. Yes. This is antiferromagnetic Hall effect, first published in a Russian journal, but then it was published in a translated journal. So people were wondering if Hall effect in this material scales with L or it scales with M. And what they did, they performed measurements as a function of magnetic field. And if it scales with magnetic field or magnetization, the dependence should be like this. But if it scales with L, the dependence should be with saturation. That's why, based on this, they claimed this is antiferromagnetic Hall effect in hematite. Well, the next question, of course, since we do optics, this is what I just explained you about Hall effect in hematite. You can talk about diamagnetic, paramagnetic effects, ferromagnetic effects, or anomalous Hall effect in hematite, antiferromagnetic Hall effect. But also, using similar approach, we can basically analyze light-matter interaction. So instead of J current density, we will use D, vector of electric displacement, E, electric field of, so to say, voltage that we apply to the sample is substituted by the electric field of light. And instead of sigma, we will use epsilon. And thus, we treat this light-matter interaction. And we see that due to antisymmetric part of epsilon, we can expect so-called magneto-optical Faraday effect. And very similar way as we did in this case, we write three terms which are allowed by symmetry for magneto-optical Kerr effect in materials like hematite. And then we can expect that in some of these materials there would be contribution which is proportional to the antiferromagnetic vector. And again, so then in order to measure this antiferromagnetic Hall effect, well, we basically measure polarization rotation. This polarization rotation would be measured as a result of different refraction coefficients for right and left-handed circularly polarized light, which can be expressed via antisymmetric part of the dielectric permittivity. And you can ask, well, why don't we measure, why don't we figure out if we take a material where this term is allowed by symmetry, can we measure antiferromagnetic Faraday effect? And again, the field is very old. So that's a paper from 1981. Professor Pisarev, as you can see here, was involved. And they took orthoferrites and they were asking themselves if they measure Faraday effect from weak ferromagnet, which is in this case orthoferrite. This is antiferromagnet with Dzelashinsky-Marie interaction. By symmetry, there are three terms allowed to contribute to the antisymmetric part of the dielectric permittivity. And they did the very same trick. They measured Faraday effect as a function of magnetic field, and what they saw, the Faraday effect scales with magnetic field differently as one would expect from magnetic field-induced and magnetization-induced Faraday effect. That's why in the conclusion they stated that existence of antiferromagnetic Faraday effect, however, presupposes the existence of non-equivalent sublattices since antiferromagnetic components of the Faraday effect vanishes in equivalent sublattices. So as you can see, the physics where people pay attention to the physics of detection of antiferromagnetic vector and looking at the effects which are linear with respect to the antiferromagnetic vector already for a long time. It's a very interesting subject, but still many things have been done before. We shouldn't forget about it. And of course, chromium dioxide, chromium 203, that's another interesting material that people were working with from the very beginning, nearly from the very beginning of antiferromagnetism. Here, the situation is unfortunately different. There is no term by symmetry which allows you to detect antiferromagnetic Niel vector if there is no external perturbation. You can have contribution to the antiferromagnetic Niel vector. Sorry, you can have a contribution to antisymmetric part of the dielectric permittivity, which is proportional to the antiferromagnetic Niel vector if there is external electric field or any other vector which acts on the sample with this, and this vector must have the symmetry of the electric field. For instance, at the surface. So at the surface, the center of symmetry is broken. We can talk about, so to say, effective magnetic field at the surface pointing along the normal to the surface. And this effective electric field can help us to detect antiferromagnetic vector in chromium 203. And here we show the result of the measurements already in our lab. But actually, this was the people have been playing with electric field-induced Faraday effect in chromium 203 before. And you can see that we see the signatures of 180 degrees of antiferromagnetic domains in this material, measuring polarization rotation. You go above the Niel temperature, the contrast disappears, then you come again below the Niel temperature, and we see that domains build up again. As I said, quite old subject, and then we hope to see more about materials with a point group of chromium 203 and also other point groups which belong to the class of antiferromagnets from the talk of Thomas today. And anyway, with this, I think I was able to convince you that the problem of detection which is linear with respect to antiferromagnetic vector, is not a real problem today. So there are enough means, enough methods that allow you to detect antiferromagnetic Niel vector and distinguish 180 degrees antiferromagnetic domains. Not necessarily in nonlinear optics, as many people claim. You can do it in linear optics. In some materials, you can even expect Faraday effect. Apparently, these materials are all weak ferromagnets. And then we go to the next question. Then, how to control antiferromagnetic spins? Well, how to control antiferromagnetic spins, and the third question would be how to do this ultra-fast. Apparently, good thing here, if you start with the third question, you will understand also that the second one is not that difficult. Because, well, imagine you excite the material with very short, very intense stimulus. And as we all know, this stimulus will bring the medium into strongly non-equilibrium state. But apparently, everything what we know about antiferromagnet, like it has zero magnetization, we describe this in macrospin approximation, it's all valid for thermodynamic equilibrium. Once you excite this, when you bring it out of thermodynamic equilibrium, it would be different material. With non-zero magnetization, we can expect nonlinear dynamics. And also in my talk, I would like to show you we can expect new channels of spin-lattice interaction. And also macrospin approximation will fail. So basically, the conventional way to describe spin dynamics in antiferromagnets using antiferromagnetic Niel vector give you wrong results if you're sitting at the ultra-fast time scale. So these are the examples of phenomena which I would like to show you today. And starting with the first one, magnetization is not zero. This is, well, it's a very trivial question. Apparently, it was so trivial that Professor Zvezin and Professor Mukhin even didn't, when publishing paper in 1981, didn't even bother to publish it in the English journal. So published in Russian journal, so I translated for you. This is a new nonlinear dynamic effect in antiferromagnets. So they analyzed iron borate, so the material with a very similar symmetry as hematite. And what they showed, they modeled dynamics of spins in an antiferromagnet by modeling antiferromagnet as two ferromagnets with magnetizations M1 and M2. Sorry, that's a misprint there. And we introduced an antiferromagnetic Niel vector. Then they solved coupled Landau-Lifshitz equations. And what they showed, that actually, even if magnetic field, there is no external magnetic field applied to the sample, magnetization in the sample can be non-zero if the vector product of the time derivative of antiferromagnetic Niel vector and Niel vector itself is not zero. So basically, if we have oscillations of spins, coherent oscillations of spins in an antiferromagnet, we can expect that magnetization is not zero. Another interesting observation and that work was that if you write equation of motion for the antiferromagnetic vector, where here we will have a second derivative of antiferromagnetic vector, sort of say coordinate or generalized coordinate on the left side, and then on the right side you expect to find driving force. Driving force, which we find here, is not magnetic field. Well, it's magnetic field in the terms like the larger the magnetization, the more important magnetic field can get. But for any antiferromagnet, even if there is no magnetization, there is a driving force, but this is not magnetic field itself, but time derivative of magnetic field. So although in the ground state, magnetic field cannot effectively affect antiferromagnetic vector, if the time derivative is not zero, spin dynamics can be driven. So two important conclusions that we can draw from this paper is that while spins and antiferromagnets are not sensitive to magnetic field, they can be controlled by time derivative of it, and coherent spin oscillations and antiferromagnets can induce magnetization. And so there were a number of papers. So these are theory papers, and then a group of Tobias Kamfrat demonstrated, and Takuya Sato demonstrated that actually if we have coherent oscillations of spins in nickel oxide, that magnetization can be induced in the case of, well, unfortunately, that's not directly seen from experiments, but in theory, you see that you excite spins not by magnetic field, by time derivative of magnetic field. Okay, so then I see that I hope to hear more about the consequences of magnetization dynamics in nickel oxides, also in talks of Enzo and Joe. where if you then I anticipate that if you they will talk about experiments that if you put platinum next to an antiferromagnet, oscillating magnetization will induce spin current into platinum, and we can expect terahertz emission in particular. Next question, nonlinear spin dynamics. So there are many people claimed nonlinear spin dynamics, and also students got very much excited that they come to me, then they say, we see nonlinear spin dynamics. So my answer in this case, sorry, I'm maybe too tough PhD supervisor, I'm sorry for that. Say, listen, if you claim nonlinear spin dynamics, then don't show me a qualitatively new effect. You're someone like who won lottery but forgot to pick up the prize. So what is the new thing when you talk about nonlinear spin dynamics? New thing here is that if nonlinearities really play a role, then you should see that 1 + 1 is more than 2. Do we see it? Let's have a look. So we take iron borates. So that's this is weak ferromagnet. It's a magnet with Delachinsky-Marie interaction. So it has two canted antiferromagnetically coupled sublattices. It is described then by, you can describe this by magnetization 1 of one sublattice, magnetization 2. But the same magnetic structure can be described by two mutually orthogonal vectors, antiferromagnetic vector and magnetization, obviously. And spin dynamics in this material is characterized by two modes. One is called quasi-antiferromagnetic, and this is associated with oscillations of magnetization in length. And another one is called quasi-ferromagnetic, and this is actually, it resembles ferromagnetic resonance. That's why it's called quasi-ferromagnetic, because it's associated with precession of magnetization around magnetic fields. So then you can, as I said, since magnetization here is small, but it's not zero, we can easily turn sample into monodomain states, although it's an antiferromagnet, and magnetization dynamics here is described by antiferromagnetic equations of motion, equations of motion for antiferromagnetic vector. We can turn sample into monodomain states. We can have nice measurements of Faraday rotation, which is proportional to antiferromagnetic vector. And what we do here, we excite iron borate with a strong terahertz pulse, and which has electric field reaching half megavolt per centimeter. Here is the time trace of this terahertz pulse, and this is the spectrum of this terahertz pulse. So we excite this material with terahertz. This is dynamics that we see. We measure Faraday rotation as a function of time delay between pump and probe. We clearly see two modes here. We do Fourier transform. We indeed see confirmation of our intuitive feeling. There are two maxima. One at the frequency of ferromagnetic mode, another one at the frequency of antiferromagnetic mode. We do confirm this hypothesis by measuring frequencies of the modes as a function of magnetic field. One goes to 0 when magnetic field is 0. Another one is not sensitive to the external magnetic field. But surprise came when we look at the dependence of the amplitude of these modes as on electric fields of terahertz. And then if one of these modes is linear, scales linearly, another one scales quadratically. So this quasi-ferromagnetic mode scales quadratically. Well, interesting, non-linear. Well, let's check if 1 + 1 is more than 2. Then what we did, we took 2 terahertz pulses. So we excited this material with 2 terahertz pulses with equivalent spectra. So these are the spectra of terahertz pulses. And this is a result of more than 24 hours measurements. As I said, the field is old, but these experimental results make me feel even older. So like this was not possible when I was a PhD student, because with this our data files were a few kilobytes, and here is the terabytes of data. This be accumulated fully automatic experimental setup. It's still possible. Fortunately, it's possible. We have talented PhD students who can do this. Here we show time delay between pump and probe. And here you see delay between pump, and color code shows the amplitude of the oscillations. So you can see here already that something periodically changing. And interesting thing here that I picked up a few dependencies for you. You can see that obviously 2 modes, quasi-antiferromagnetic at very high frequency and quasi-ferromagnetic at lower frequency. The period of quasi-ferromagnetic mode is 50 picosecond, but if you change the distance between 2 pump pulses just by 1 picosecond, which is nothing compared to 50 picosecond, the amplitude changes dramatically. Then you change again by 1 picosecond, and it's again changed. So something is going on here. So what we did, as I said, we are now checking if 1 plus 1 is equal to 2. So we take full signal induced by 2 terahertz pulses, then subtract signal induced by first terahertz pulse only, and the signal induced by second terahertz pulse only. And then if 1 plus 1 is equal to 2, we should have 0 here. And if it is not, that's interesting to see what we have. So we did this in time domain. Then we make Fourier transform. And this is the result of Fourier transform. Excitation frequency corresponds to the frequency which is associated with time delay between 2 pump pulses. And detection frequency corresponds to the frequency associated with time delay between pump and probe. And here we use notation with negative and positive frequencies. So basically, if you look at this quadrant, you just see one maximum at the excitation frequency of antiferromagnetic mode and detection frequency of ferromagnetic mode. So basically, interpretation of this observation is very simple. The first terahertz pulse excites quasi-antiferromagnetic mode, and the second terahertz pulse interacts with coherent magnetic state here, which is obviously different than interaction with the medium in the ground state, because magnetization can be larger here. And it interacts with a pulse of larger magnetization, can effectively excite quasi-ferromagnetic mode via mechanism which is very similar to stimulated Raman scattering, but here only involving magnetic states. So basically, this experiment shows that if you're talking about nonlinear dynamics, then you can expect that 1 plus 1 is more than 2. And this is another very interesting development from a group of Professor Nelson from MIT, that they also work with orthoferrites in this particular case, and they observe different types of nonlinearities, which resembles more some frequency generation. The next question is new channels of spin-lattice interaction. So here I would like to talk about cobalt fluoride. It's also antiferromagnets, also very old antiferromagnets. So people studied piezomagnetism in this material already in the 60s. It's compensated antiferromagnet with no net magnetization with antiferromagnetic vector along z-axis. So we pump this material with strong terahertz pulse and detect, hope to detect magnetization dynamics measuring Faraday rotation. And just a moment. That's how it worked. Also doesn't work. Just a moment. Yes. So we again perform double pulse excitation. Here, the delay between 2 pump pulses is 0. Here, the delay between 2 pump pulses is 20 picosecond. Here's 10 picosecond. Then, if you see the delay between 2 pump pulses, 10 picosecond, dynamics is clearly different than if the delay between 2 pump pulses is 0 picosecond. Basically, they overlap one with another. So something else is going on here. So we again do the very same trick. We check if 1 plus 1 is more than 2. We take the full signal, subtract signal induced by first pump pulse only, signal induced by the second pump pulse only, and then we make Fourier transform of the result, and we find a very interesting thing, a maximum at the excitation frequency that corresponds to the frequency of magnon, and detection frequency that corresponds to the frequency of phonon in this material. So basically, if you interpret these results, so basically what happens is the first terahertz pulse excites magnon and generates coherent magnetic state, and the second terahertz pulse interacts with this coherent magnetic state and excites phonon. And obviously, this is a question of fact that this is the matter of fact that 1 plus 1 is more than 2, because otherwise we will have that maximum there. And here we have a very interesting development also. We realize that if you tune frequencies of magnon such that frequency of magnon is taken twice is exactly frequency of phonon, it would correspond to the condition of Fermi resonance, so-called Fermi resonance. And in this particular case, we will have Fermi spin-lattice resonance. And tuning with external magnetic field, tuning magnon frequency, we can go into the resonance condition and out of resonance condition, and in this way control spin-lattice interaction. And these expectations fortunately worked. Well, unfortunately, in order to do these experiments, you need narrow band. Unfortunately for us, and fortunately for Telber facility in Dresden, you need intense narrowband excitation. So that's why we did this experiment. We excited with narrowband terahertz pulses such that we excite only magnon and nothing else. So phonon is not touched by this excitation. And then we perform measurements as a function of magnetic field, and then we can see that phonon clearly has maximum at the non-zero magnetic field, and it's very close to the frequency where magnon frequency taken twice is the frequency of phonon. Something we don't completely understand. We see clearly the maximum, so we can control the efficiency of excitation of phonon. We don't quite understand these spectral features here with the dip, that maximum is slightly shifted compared to the condition where frequency of phonon is equal to 2 frequencies of magnon. So we perform simulations, we have some ideas about it, but for sure this experiment clearly shows that we can control efficiency of spin-lattice interaction, and as a matter of fact, if you realize this condition, this is Fermi spin-lattice resonance. So this is something that we try to claim, and well, experiment shows it is true. Final question. So I think I'm running faster now than I was supposed to, but we will have more time for discussion now. Macro spin approximation fails. Okay, so macro spin approximation. So we used to describe magnetization dynamics in terms of antiferromagnetic Niel vector. And for instance, if you want to describe light-matter interaction with an antiferromagnet, then the very first term, which is allowed in absolutely every antiferromagnet and describes light-matter interaction or light-spin interaction in antiferromagnets, would be termed like this. So this is the rest of free energy, and this is the very first term in thermodynamic potential, that the term of the lowest order, which describes interaction of electric field of light with spins. As I said, the condition is that it's allowed in every single antiferromagnet. And then we can write here a term which is proportional to the square of antiferromagnetic vector, and of course it should be proportional to the square of electric field, otherwise by symmetry we will not get scalar here, which is absolutely necessary if this is thermodynamic potential. Well, then in many experiments, people discuss, so to say, excitations at the center of the Brillouin zone. But in antiferromagnets, you can also expect excitations at the edge of the Brillouin zone. So like if you take very short laser pulse, not as short as attoseconds, we saw last week, but even if the pulse is as short as 10 femtoseconds, the spectrum is broad enough such that in this spectrum you can find frequencies omega-1 and omega-2 such that their difference will be equal twice the frequency of the magnon at the edge of the Brillouin zone. So basically, with this excitation, we can realize mechanism of stimulated Raman scattering with excitation, simultaneous excitation of two magnons at the edges, two edges of the Brillouin zone, and one magnon will have k vector point in one direction, second magnon will have k vector points in the opposite direction. It's absolutely necessary because, as I said, we must have scalar here, and then here we must get something, and also scalar which doesn't depend on coordinate, obviously. Then here, two vectors, two antiferromagnetic vectors should be then taken such that this thing doesn't oscillate in space, so to say. That's why k vector and this k vector should have opposite signs such that they sum will be zero. So basically, you can say it's a law of conservation of momentum, nothing else. So then we look at this term and we say, well, according to stimulated Raman scattering, we can expect it works. So we can excite two magnons at the edge of the Brillouin zone. Term which we'll describe this process would be like this. Electric field at omega-1, electric field at omega-2. Omega large is the frequency of magnon at the edge of the Brillouin zone. K is a vector of the magnon at the edge of the Brillouin zone. Fine. Then you can detect these two magnons at the edges of the Brillouin zone, looking at the dielectric permittivity. Simply paying attention to the fact that the electric permittivity, the second derivative of the thermodynamic potential with respect to the electric field of light. So then you can see as a result, there must be effect which is quadratic with respect to the antiferromagnetic Néel vector. So we took rubidium manganese fluoride, very symmetric antiferromagnet with very small magnetic anisotropy. We excited with short femtosecond laser pulse, 10 femtosecond short. Then we probe spin dynamics in this material, measuring birefringence induced by magnetization dynamics, measuring epsilon practically. And what we see very fast dynamics, which disappears above the Néel temperature, which shows that this is associated with magnetization, with the spin dynamics. The frequency of the dynamics is exactly the frequency of the magnon at the edge of the brilliant zone taken twice. That's all fine. It's 2 magnon excitation. And something that puzzled us a lot, and we were busy for more than 1 year, actually for 2 years long, and we found that the maximum signal is in the configuration when the electric field of light is exactly along the antiferromagnetic Néel vector. So basically it means by symmetry, if you see oscillations of electric field of light, and this is exactly what we measure, so either polarization, we measure either polarization, rotation, or ellipticity, but they are connected. So if the polarization state of light changes at very high frequency, in this configuration, the only spin dynamics that can cause these changes would be oscillations of antiferromagnetic vector around equilibrium. If it changes in length, it will not affect the signal because the material is anisotropic. And then antiferromagnetic Néel vector can have either longitudinal dynamics or transverse dynamics. So it must be transverse dynamics, and it should have this high frequency, which is nonsense, obviously, because this frequency is twice larger than the highest frequency in the spectrum of magnons. How can it be? And actually, we realized that at the edge of the brilliant zone, you may have problems if you describe spin dynamics in terms of antiferromagnetic Néel vector. You better use spin correlation function. So basically, you go along chemical bonds and you calculate spin to spin correlation function, and it would be a quantity which is quadratic with respect to spin. It will have the very same symmetry as L square, but have different physical interpretation because it's not associated with the direction of spins. It's associated with correlations of spins along one or another direction. It can also induce linear birefringence in a medium, which we detect. So obviously, this shows that at the edge of the brilliant zone, approximation of antiferromagnetic Néel vector fails. In the case of antiferromagnets, it's called macrospin approximation very often, but it's, well, unfortunately, it's very often also misinterpreted. We have to correct ourselves. What we mean, it's a failure of, we don't say that macromagnetic simulations will fail. We don't claim that atomistic simulations will fail. We don't do them. What we claim, if you describe spin dynamics at the edge of the brilliant zone, you will be in danger if you use L. And then these are the conclusions, the summary about ultrafast magnetism, which I brought. Why the field is interesting? Because everything what we know about antiferromagnets so far, or almost everything, is about thermodynamic equilibrium. Antiferromagnet out of thermodynamic equilibrium is practically different material with non-zero magnetization, nonlinear spin dynamics, new channels of spin-lattice interaction. When superposition fails, when 1 + 1 is more than 2, and this is very good news actually, that we can, in the control of spins with the help of Terahertz, you have to be careful with macrospin approximation, which in the case of antiferromagnets is the approximation of antiferromagnetic Néel vector. And something that keeps me intrigued in this field, and I still don't have an answer. Look, if we now know how to distinguish two speed states with antiferromagnetic Néel vector up and down, so we can assign to these two states, or to 280 degrees antiferromagnetic domains, for instance, state 0 and state 1, so we can use them as the bit states. So these two bit states have equal energies, equal entropies, but also in contrast to ferromagnets, equal angular momenta. So if you find a fully coherent way from one state to another, and fully coherent means entropy simply doesn't have time to increase, looking at this picture, I would say it would be not only ultra-fast switching, its switching doesn't cost any energy. I don't say it's possible, I just say it's something that keeps me thinking. For sure, physics is much more richer than this, but this is exactly what I want to state with this slide. I think, although it has very good, very intriguing motivation, there's even more interesting physics here. There's a terra incognita of modern science, which I think everyone is welcome to enter. A lot of interesting things. And at the end, I would like to thank all my co-authors from many institutes of my group funding. And also, I just came across, basically, I was told by, I was asked by colleagues to promote new journal of Nature Publishing Group on Spintronics. And this is open access journal, and at least as they told me, that for the first 2 years, they will not charge for publishing there. So they're now collecting topics. So my question is, why don't we synchronize our efforts in Terahertz Spintronics and try to make an impact on this journal, right? And then a journal will make impact on the field. And that's how the things will evolve. Okay, and at this, I would like to stop, and I would like to thank you for your attention. Thank you very much.